Good morning, everyone. So we're going to pick up at the end of the Chapter 9 notes from the Section 9.6. The final two sections in Chapter 9, 9.7 to 8, we'll get to those after the midterm. So we're just covering through 9.6. And so these are the last couple slides from the sections on 9.6. And so what we want to do here is try to get a picture of what's going on with resonance delocalization. We're talking about resonance in Chapter 8. A molecule that does this is nitrate ion, so the ion being shown here is NO3 minus. And you might recall one of the Lewis structures we had for nitrate looks something like this, where we have lone pairs around the O's, but we end up with one double bond. And so we have this one double bond that we could then draw two other Lewis structures that are equivalent. So we could draw this double bond over here, so we can have the resonance to this structure here. And then we can have the resonance over to this position here with the double bond. So we have three equivalent Lewis structures that we can write for nitrate ion. And so whenever we have the possibility or the situation where we can write equivalent Lewis structures, the real structure looks like the average of the composites. You might recall that the real structure will look more like this, where the three bonds end up being identical to each other, and we don't really ever have a double bond versus two single bonds. And so this is a hard concept, I think, for students to understand sometimes. This isn't like a really fast equilibrium situation. This is just at all times, nitrate will manage to look like this structure here. Now, the way that it does so, or a model that can show you why this happens, is if you think about nitrate or the nitrogen atom and all of these structures here. So in all three cases, we're going to think about that nitrogen being sp2 hybridized. And so because it has three total domains. And so all three of the Lewis structures are equivalent. They all show a nitrogen that would be sp2 hybridized. And so then that lets us think, okay, if we have this double bond here, or wherever that double bond is in our structure, we can sort of picture that we'd have what looks like the p orbitals overlapping to make that pi bond. And so just like any double bond, we think it's a sigma bond. So we end up with the sigma overlap, so that's our sigma part of the bond. And then the second part of the bond, the pi bond, or what makes it a double bond is the ability to have that pi bond. Well, if you imagine we resonate over to this structure here, then we'd have the pi bond here. And then if we resonate over to the double bond being here, then we'd have these orbitals aligning to make the other double bond. So in other words, if you can picture those p orbitals all simultaneously overlapping together, if we can have a situation where we get that overlap, but in one kind of structure, so that ends up being the model for delocalization. So the way we get this extra pair of electrons here to spread across the other two bonds at all times is by the simultaneous overlap of those p orbitals that make that pi bond possible for those double bonds that we think are localized. So localization is thinking you have a double bond just here and not here and here. So thinking you have the double bond here, that's what localization looks like. That's what we call localized double bond. But delocalization is the picture you get in resonance, where you spread those extra pair of bonding electrons across all three of those bonds simultaneously. So instead of having one double, two singles, we kind of have three single bonds plus like a third of a bond extra at any given moment. So that's why we called this bond, if you recall, a 4/3 bond, because we're taking in terms of the counting of bonding pairs, I think this is pretty straightforward. We're taking 1, 2, 3, 4 bonding pairs of electrons, and we're spreading those across the 1, 2, 3 bonds between nitrogen and oxygen. So we have 3 NO bonds. We have 4 pairs of electrons being spread across those bonds. And we'll see when we get to some review slides that we can sort of start to rank order bond lengths. Single bonds are longer, double bonds are shorter. A 4/3 bond would be in the middle. So we can start predicting bond length trends with the idea, if you recall, that single bonds are longer than double bonds or longer than triple bonds in terms of their length. And so a single bond has a bond order, so it's one pair spread across one bond. A double bond is 2 pairs spread across 2 bonds. A triple is 3. So our 4/3 would be right there in the middle in terms of our bond length. So we'd expect it to be a little shorter than a single bond, but longer than a double bond. And we'll see a few more examples of that as we continue. But the key part here from chapter 9 is you get a picture, you get, I think, a nice picture from the overlapping of those p orbitals simultaneously to show you how it's possible that this molecule spreads that electron pair out at all times, and hopefully reinforces the idea that just because we can write a Lewis structure doesn't compel the molecule to behave that way. So just because we start with a Lewis structure that looks like, say, this one here, and we realize, oh, we could have written this one and this one, that the real molecule averages out into this structure. So this ends up being the real structure of nitrate, and then the delocalization model is how that happens. Other molecules do this. An important molecule in organic chemistry is benzene. So benzene, and to even give you a quick little preview of organic chemistry, is that the vertexes in a structure are assumed to be carbon atoms. So the way you'll learn this a lot if you take 2510 and 2520. But whenever you have like a vertex, like if we have this here, the vertex points are all carbon atoms, and then you just simply have enough hydrogens assumed to give that carbon 4 bonds. And so if I kind of come back to this for a minute, so if I'm drawing something like this, I have a carbon in each vertex, and I have to have enough hydrogens to give that carbon an octet. So this is just a quick little preview. I don't think you'll ever see this on a test in terms of needing to know how to get the number of hydrogens, but the idea here is that you're just picturing at each of these vertex points a carbon atom, and then you're assuming there's enough hydrogens to give that carbon its octet, so it has 4 total bonds. And so again, you'll see this a lot next year if you take OChem. Well, in terms of benzene, we have carbons at each of the vertex points, and then we're going to have 1 hydrogen only because that gives each of the carbons 4 total bonds. So if you look at any one of the carbons, we have 1, 2, 3, 4 bonds. So each carbon with 1 hydrogen on the outside of the molecule has its octet. And so, but if you then kind of, let's erase the hydrogens and those carbons so we can look back at our structure. If you notice this structure here, I can move these double bonds over to this structure here. So I just simply have realized that there's 2 equivalent Lewis structures that I can write that are equivalent to each other. And so this is another molecule that should show resonance. And so the idea here is that each of these centers is an sp2 because we have 3 total domains. I'll write one of the hydrogens in just so you can make sure you see you have 3 total domains. You have domain 1, domain 2, domain 3, and then each of those centers should be an sp2. And sp2 leaves behind 1 unhybridized p orbital. And so if you leave behind an unhybridized p orbital, that's the model that gives you your double bonds and gives you that pi bond. And so we have pi bonds here kind of showing our 3 pi bonds. Well, then we shift them over, and then we get these pi bonds here that look very similar, but they've just shifted over into the structure. But the real molecule doesn't go from, let's call one A and the other B. The real molecule is not going from A to B and back and forth. The real molecule says, hey, why don't we just simultaneously overlap all those orbitals and come up with like one set of orbitals that simultaneously overlaps all 6 of those p orbitals, and that's the delocalization picture. So that's why a lot of times we write benzene structure with like a ring in the middle. Another way of writing this structure that I think makes a little bit more sense is if you do like a dash line, because you're kind of saying with the dash, like you're saying you don't have quite a double or a single, you're actually right in the middle, because we're just averaging out having a double versus single. And so if we want to get the average bond order and say, okay, for this bond here, what's the average bond order? The way I might think of that calculation would be just the count that I have 1, 2, 3, 4, 5, 6, 7, 8, 9 electron pairs. So 9 total pairs of electrons, counting the single and the double bonds between all the carbon atoms in the structure. And I'm going to divide that by the number of bonds. And so I have 1, 2, 3, 4, 5, 6 carbon-carbon bonds. So I have 6 carbon-carbon bonds and then 9 bonding pairs. And I think that makes sense. Like you're averaging out a double versus single, that averages out to a 1.5 bond. And so the bond lengths of carbon and benzene are all the same. I think that, to me, that's the key detail. Is if, and I think that's the important question we would ask on a test like this. We would say, you know, either given one of these Lewis structures or both of these Lewis structures, or given a model like this where you're averaging out the bond, do you expect these carbon bond lengths to all be the same as each other? And the answer is yes. Especially if we show you just like say one of the Lewis structures and say, say we give you one Lewis structure and say consider resonance in the molecule benzene. Are all the carbon-carbon bond lengths the same length, or are 3 of them shorter, 3 of them longer? And it's not 3 shorter, 3 longer. We really don't have 3 double bonds, 3 single bonds in the molecule. We really have 6 bonds that are averaging out to be about 1.5 bonds. Another question we could ask is, what do you expect the bond length to be? Well, we'd expect it to be, in terms of a carbon-carbon single bond, shorter. In terms of a carbon-carbon double length, longer. So we expect it to be right between the length of single being a longer bond than a double, and our 3 halves being in the middle. And sometimes this is confusing, but just making sure you see a double bond has a bond order or a bond type of 2, a single of 1, so 3 halves is right in the middle. Okay, so this question here is just meant to kind of show, okay, like how can we count things like resonance structures? You can kind of compare this with nitrate. So like if we had nitrate, how many resonance structures does nitrate have? We had 3 structures for nitrate. And so we might even consider, if we're looking at nitrate, the answer to this question would have been 3. For benzene, we have these 2 structures. So we can write 2 different equivalent resonance structures for benzene. So it has 2 resonance structures. What's the average bond order of the carbon-carbon bonds? I think the way to do this is either picture just 3 of the atoms and how it averages out to be a bond and a half, or to calculate them all. And so if we calculate for all the carbon-carbon bonds, then that's how we got 9 total pairs of electrons across 6 bonds for a 3 halves bond order. And I think you can see that a few different ways too. If you just picture 3 of the atoms, where you go double over single, on average, we're getting a bond order for the carbon-carbon bonds to be 1.5. Are all the carbon-carbon bond lengths in benzene equal? Yes. So all the carbon bond lengths are equal. It's never that 3 are shorter, 3 are longer. And then a question for chapter 9 is, how many electrons can we say are in this like delocalized pi system? So a pi system are all the pi electrons that are participating in this system. So I think for benzene, this is actually a pretty easy question. For nitrate, it's actually a little bit trickier. So let's look at benzene real quick. It's just these electrons, but in the double bond. So it's just the pi electrons. And so the pi electrons are just the 2 electrons in each of those pi bonds spreading across over to here. And so the total number of pi electrons is going to be equal to 6. So why is this 6 again? Well, it's because we're looking at the pi bonds here. And there's 3 of them. There's 3 pi bonds in the molecule, 2 electrons in each of those pi bonds. So we have 1, 2, 3 pi bonds. And those are the electrons in that pi system for benzene. If we were to ask this question for nitrate, it's a little trickier. It's really, if you ask me, it's more of an interesting question for benzene than it is, because you can kind of see it more. You can kind of see all those 6 electrons are what are spreading across the molecule. In the case of nitrate, you have these 2 electrons that move in, these 2 electrons that move out, and then these 2 electrons that later move in as well and kick those out. So you actually have 6 electrons that are participating in this system. So you have 6 as well for nitrate. So you don't have 6 pi bond electrons, but you have 6 electrons that are participating in the entire system overall across the molecule. So it's a weird, to me, it almost is a meaningless number for nitrate. For benzene, I think it makes a little bit more sense why we would ask about the pi system. And then when you get to OChem, you'll learn about all different kinds of larger molecules that have even more pi bonding electrons. You'll learn how there's a difference between having like 4 versus 6 versus 8. There's something really special about having 6 or 10 or 14. There's something bad about having 4 or 8, but we'll let OChem kind of fill in those details for you later, for those of you who at least take OChem. Okay, so we'll wrap up the coverage of chapter 9 for us, at least through 9.6 for midterm 4. So at this point, we can get into some review problems. I'm not sure how far I'll get, but there's a chapter 7 packet. There's a chapter 8 packet. It's actually a really short chapter 8 review packet. But a lot of chapter 8 Lewis structure questions are embedded into chapter 9 topics too. So I think we'll hit a lot of review aspects of Lewis structures when we look at a lot of chapter 9 questions in our chapter 9 packet. And then towards the end of the chapter 9 packet, there's also like a couple chapter 8 questions and a chapter 7 question. And so then also just a reminder, if you didn't get to attend Dr. N's review last night, go to her YouTube channel. The link's to my announcement from last week if you want to watch her review. I have a review on Monday. Again, no class Monday for for Veterans Day, but I'll do a Zoom review from 1:30 probably till about 3. If we get through a lot of these questions, I'll put up another packet of questions that I can do, and I'll also take questions first, so if you guys have specific problems or questions, we can definitely work on those topics first. Okay, previously I had done this question before, but I wanted to come back to it just so that we can remember kind of the aspects of ranking size from chapter 7. So when I'm ranking the size of atoms that are uncharged, that's where I use my periodic trends using the periodic table. So my periodic trend for atomic radius is that I get a decreasing atomic radius from left to right, and then an increase in size from top to bottom. And so the left to right trend is coming from the effective nuclear charge, increasing from left to right. So as you go from, say, lithium across to neon, you have a constant number of core electrons. The thing that's really changing is the nuclear charge is going up. So neon experiences a really high effective charge because it has a high nuclear charge and only 2 core electrons in the way, so it experiences really high charge, makes it really small. And then lithium experiences only about a +1 effective nuclear charge because it has that core 2 electrons in the way, but a much lower Z, a much lower total nuclear charge. So lithium, really low effective charge, so it's a big atom. And then neon, really high effective charge, so it's a really small atom. And then if you imagine going from lithium to sodium, you reset the charge. So sodium's charge goes back to being low. So you go from lithium, low charge, across to neon, high charge, come back to sodium, back to a low charge. And so lower effective charge for sodium, that's our periodicities coming from the effective charge resetting with each row of the periodic table. But then we do get an increase in size, but just due to having more and more electrons as you go from top to bottom. So having 3 for lithium, 10 total, or 11 total for sodium, 19 total for potassium, we're just increasing the electrons, increasing the size from top to bottom. And so this is the trend that we use for K versus Cl because we can rank K. We might use the common potassium and chlorine aren't in the same row. If you notice, potassium's a row down. So we might want to compare the 2 of them to sodium. Potassium, of course, is bigger than sodium from the top to bottom trend. And then sodium from the left to right trend is bigger than chlorine. And so that helps us see for sure that potassium is bigger than chlorine. We could have also done the trend relative to bromine. The potassium has to be bigger than bromine from left to right trend because they're in the same row, the periodic table as each other. So we know as you go from potassium to bromine, size decreases. And then chlorine from top to bottom, chlorine has to be smaller than bromine because it's towards the top of that row of the periodic table. So the thing that we wanted to do to compare the sizes of K versus Cl is just find a common element, either from left to right or from top to bottom, that we can make an easy comparison so we can know for sure how to rank the relative sizes of potassium and chlorine. There's some bad questions. You might wonder, well, what if we said, well, what's bigger, what's bigger, sodium or bromine? Do you see how this is a tough question? You know, like some pairs on the periodic table you can't rank because you're like, well, sodium's bigger than chlorine, but bromine's bigger than chlorine. I don't know which one's bigger than the other. So this is a bad question. So there's a lot of bad questions in terms of ranking size that we can't ask you. When we ask you a size ranking question, we have to be careful to make sure we're giving you things that can actually be ranked for sure, that you know an easy way just using these trends to rank their size. Now, when we throw charges on the atoms, we're using a whole different ranking system when we have charged ions. What we want to think here is how many number of electrons do these ions have? K plus, potassium has 19, take 1 away, that has 18 electrons. Chlorine with 0 charge, if we're looking over here, so we have 19 electrons here, we have 17 electrons for chlorine. If you add an electron to go to Cl minus to chlorine, that's 18 electrons as well. So these are isoelectronic, meaning they have the same number of electrons, the same electron configuration. And so if you're an electron in an ion, and you're being pulled in by the nucleus, that's why you're kind of like attached to that particular atom or you're spinning around that atom. Are you going to be drawn in closer if the charge is higher or if the charge is lower? If you're that electron, you're probably going to move in closer if that charge is higher. So what we want to rank is the number of protons in the nuclei of these atoms. So we want to compare the number of protons. So the size is going to decrease. So the size of the ion will decrease with increasing protons. So as proton count goes up, with the same number of electrons, you can pull them in more closely. And so that's going to make K plus be smaller than chloride ion. And so which atom or ion in each pair is the smallest? And so we have chlorine when we're ranking uncharged and then we have potassium plus when we're ranking their ions. And so let's also come back to this detail that K plus has to be smaller than K. So anytime you have a cation, it's smaller than its neutral counterpart. And you can do this as well. You can say like magnesium 2 plus is smaller than magnesium plus, which is smaller than magnesium neutral. So every time you lose an electron, you're losing negative particles that repel. You're making the ion smaller. And so then, so this trend can be said for cations, and then obviously the opposite would be true for anions. If we compare the size of F versus F minus, if you add an electron, you add to the repulsions, and you increase the size, so the anions are larger than their neutral counterparts, cations are smaller than their neutral counterparts. So take electrons away, reduce repulsions, reduce size, add electrons, increase repulsions, increase the size. Okay, and so if you're comparing, Cl, of course, same thing. So chloride's bigger than chlorine. And so the case for potassium versus chlorine, potassium bigger than chlorine, but add an electron to chlorine, it grows in size. Take an electron away from potassium, it becomes smaller, such that you flip their relative sizes. So K plus is the smaller ion compared to chloride. So let's look at electron configurations. So for our rules for cation configurations are that when we're thinking of the configuration, let's think zinc 0 first. So if I want to know the configuration of zinc 2 plus, let's first do zinc 0. Make sure that we start from the neutral atom first and then think which electrons are we going to take away to make our cation. So the configuration of zinc neutral from our periodic table would be a 4s2 and a 3d10. And so this is just from chapter 6. And so we have a completely filled D subshell. And so then the question, I think, would be, which of these electrons is most weakly held onto by the nucleus of the atom? And so if you're thinking of zinc, and we can put this together, zinc's element number 30, we have a 30 plus. So in terms of what zinc looks like, we have a 1s shell. So we go from 1s to 2s to 2p. I'm only going to draw 2 of the 3 2p orbitals, so I don't draw the one sticking out of the plane to make this really messy. And so that's our 2p set of orbitals. Then I have my 3s electrons. Then I have my 3p. And then my 4s is way out here. And then where are the 3d? The 3d is in the n equals 3 shell, which is right here. So my 3d is in this region between the 3p orbitals. So the 3d subshell is smaller than the 4s. So the way our subshell sizes would go here, if I'm rank ordering how close these subshells are to the nucleus, I'd have the 1s is the closest, then the 2s, then the 2p. Then I'd have the 3s, the 3p, and then the 3d, because the 3d is just closer to the nucleus than the 4s is. And so then I'd have the 4s. And so this is the ranking of my effective charge experienced by a 1s electron. So the 1s electron experiences the greatest nuclear charge. It experiences just about the entire full nuclear charge that the atom has to offer. So it experiences about a plus 30 charge. There was a slide, if you recall, that actually looked at the calculated effective charge by the 1s electrons. If you were to look at that slide, if you notice, argon is not quite 18. Argon's Z, number of protons for argon, is 18. And it would look like on that graph it's like 17.5. Why is it 17.5? Well, remember how every orbital that's bigger than 1s has still some probability of those electrons being relatively close to the nucleus? It's like on average, all the other electrons have a tiny probability that some of them are absorbing a little bit of charge before that 1s electrons can get to them. But still, the 1s are the closest to the nucleus, so overall they experience the greatest overall effective charge. Then the 2s and the 2p. Then we're just going in order that we were filling, but until we get to the 3D subshell. And then we're thinking relative size. So this is a smaller orbital. And then we have our larger 4s. So the removal of electrons is going to be in order of the weakest held onto electrons lost first. So we lose electrons first from the highest n orbital with the highest L. Okay, so not the orbital with the highest L overall, but we look for the highest n orbital. So the orbital with the highest n value, so that would be the 4. And then if we have two orbitals that share the same n value, we take from those that have the highest L. But there's only one n value of 4 here, so we take the 4s2. So our configuration for argon 2 plus our configuration for zinc 2+ is argon 3d10. Okay, and it's important just as a reminder, this isn't an anomaly. This is just the rule for all substances. If we wanted to do the configuration for like lead 2+, just to show for, how do we apply the rule highest N with the highest L, lead's L, dyslexic today, I guess. Lead is 82, not 28. So lead's element number 82. So it's in the carbon row towards the bottom. And so 82 would be the xenon configuration, followed by, and if you're not sure if it's 6 or 7, let's just count down. So after 54 is element 55. It's in the 6th row, so that's our 6s2. Then we go across the first F block, 4f14. We go across the third D shell, that's a 5d, so it's a 5d10. Then we finally get back to a P subshell for our last 2 electrons for a 6p2. And now again, like how do you remember that this is a 6p as opposed to a 5p or a 7p? Well, just remember carbon's a 2p, silicon would be a 3p, germanium a 4p, tin a 5p, lead a 6p. So that's how you can double check the count here to make sure that we're getting the right count. And then carbon's a 2s2, 2p2, so the S and the P numbers should be the same. And so then our configuration for lead 2+, which of these 2 electrons do I kick out? And it's like the 4f is a bad choice. So those are really, really close to the nucleus. So those are held onto pretty strongly. The 5e also pretty close to the nucleus, or closer to the nucleus than our N equals 6 electrons. So it really comes down to these 2 electrons here. In fact, if we were counting valence count, I would say lead only has 4 valence electrons, the 6s2, the 6p2, the outermost shell. And so I think our best choices for removing electrons are the 6s and the 6p electrons. And then which ones are bigger? The p subshell. They're further away, easier to remove those electrons. So we remove the highest N with the highest L. This is just a way of saying the largest subshell electrons are lost. So the configuration of lead 2+ is equal to xenon 6s2, 4f4, 5d10. We've lost the 6p2. Okay, so for cation configuration, start with the neutral atom, write its configuration for a 0 charge, and then think which electrons are you removing. For electron affinity, so one of the things that's helpful for us to remember is what's the difference between ionization energy and electron affinity? Well, ionization energy for something like fluorine, start over here. So for fluorine, ionization is losing electrons. So to go to F++ an electron, this would be our IE1, our first ionization of F. Our IE2 would look like F plus losing a second electron to go to F2 plus an electron. So that's ionization. And so for losing electrons, that's ionization energies. The second ionization energy for any substance is higher than its first. So as you take electrons away, you're making the ion smaller, making it harder to remove the next electron. So all subsequent ionizations require more energy than the previous. So I1 to I2 to I3, as we go, the successive ionizations take more energy. So we can write I1 would be less than I2. Another way of thinking it, I2 is greater than I1, I3 even greater. So the third ionization even higher. The removal of a core electron takes a tremendous increase in energy. And so whenever we get to the point where we're removing a core electron, we get a big increase in energy for the ionization of a core electron. So it's going to take, for fluorine, it would take removing 7 electrons. So to remove the 8th electron for fluorine would require a tremendous more amount of energy than the other electrons we've removed. But then for electron affinity, it's not entirely the opposite, because to me the opposite is flipping a reaction. So the electron affinities aren't the flipping of the reaction of ionizations, but they are the absorbing of an electron flip. So instead of losing an electron, we're absorbing an electron, going to F minus. This is electron affinity. And to be fair, we don't maybe think of it this often, but these are like the EA1s. We don't talk too much about EA2s, but the EA2 would be the energy required to absorb a second electron to go to like F2 minus. And now this doesn't make a lot of sense at F2 minus, probably not gonna form because we filled our octet, or we filled that noble gas configuration to F minus. And so this seems like this would take a lot of energy and not be something that's likely to happen. But this step here is actually favorable. Halogens have the most favorable electron affinities, and these are generally negative. for this step here, meaning it's favorable for atoms to absorb electrons, and it's the most favorable for the halogens, so we become more negative or lower. So electron affinity is decreasing from left to right, but we stop this trend at the halogens. And the noble gases are high. So the highest electron affinities are the noble gases, so they're the group of elements that restart the trend. So we decrease towards the halogen, reset high with the noble gases, and decrease from there. We have some configuration issues like we did with ionization energy that really aren't all that big of a deal, because I think the whole reason we talk about ionization energy is just to make sure that we have the thought that as you go from effective charge increasing from left to right, so you go left to right, the charge is increasing, that's decreasing our size, then the energy required to move electrons should increase. But the only thing that's weird with ionizations is we start removing electrons either from s or p orbitals as you go from left to right, or spin paired versus unpaired orbitals as you go from left to right. So we have some configuration issues that give us the ionization zigzag, if you recall, goes something like this, where we go 2 elements up, one's a little bit down, or not up as much, and we have one that's down, and then we go back up. So we have like a zigzagging trend, but for configuration issues that aren't that important to understand or explain or reproduce or expect questions on the anomalies there. I know a lot of times we ask about the anomalies, but I think this trend, we're just trying to say, okay, maybe we can understand that we're just removing s electrons in a p, then a spin paired electron as you go across from like lithium to beryllium to boron, carbon, nitrogen, oxygen, fluorine, neon. So the issue with like oxygen is it has 2 spin paired electrons, but nitrogen didn't. So there's just a slight weird non-comparison of ionization energies you go from left to right. It's like we just wanted to say attraction to the nucleus increases left to right, so energy to remove electrons should increase. But we just have different types of electrons in different situations, making this not a consistent trend from left to right. And I think it's important to note that size decreases left to right without any break in the trend. Effective charge increases from left to right without any break in the trend. It's just a configuration anomaly issue for ionization energy. And then we also then have the weird anomalies for electron affinity, but it's with beryllium and nitrogen now instead of the neighboring boron and oxygen being low, because to add an electron to beryllium means you got to put it into a higher energy subshell. So that takes a little bit more energy that you don't get back by the new negative, positive attractive force that you're adding. And then the nitrogen group isn't as favorable because you're now spin pairing an electron when you add an electron. But again, not a big detail. You're probably not going to get a question of like, why is nitrogen's electron affinity not as negative as its like 2 neighbors? That's a very deep question. But if you at least can say the trend zigzags a little bit because there's configuration issues, but generally adding an electron to a smaller atom that has a high charge like fluorine is favorable. Okay, now the top to bottom trend you can also then reason is going to be complicated. So if you say is fluorine, chlorine, bromine, or iodine best, if you remember for ionization energy, removing an electron, we had the issue, is it better to have the high effective charge for fluorine or the even higher for iodine? But iodine's really big, so you have a little bit of a bigger charge, but that valence electron's really far away. It turns out the ionization energy's highest for fluorine and decreases downward generally. If you look at electron affinity, you might say, well, what wins out? Is it the high charge for fluorine, the higher charge for iodine, or the small size of fluorine, or the big size of iodine? The answer is kind of both trends went out. Chlorine, the third row, is best. So chlorine's most negative, but there's not much of a pronounced trend from top to bottom. So the way I would recommend thinking of it is there's not much of a top to bottom trend for electron affinity. If anything, it's at the third row is the most stable. The issue with electron affinity is kind of like we take an atom, add an electron, increase repulsions. And so fluorine's so small, we add an electron, makes it really big. Chlorine, we add an electron, makes it a little bit bigger. So chlorine tends to be a little bit more negative in the electron affinity. So there's a few trends that are interesting with ionization energies and electron affinity that you might be confused by about how do you remember these, or do you need to remember those? I don't think you need to remember the top to bottom trend. So I think the best way to think of the top to bottom electron affinity trend is that there's not much of a top to bottom trend. And the one that there is, we can maybe comprehend it, but not worry so much about having to memorize or reproduce that thought on a test. Okay, so to answer this particular question here, which atom or ion requires the least amount of energy to be absorbed to lose one electron? Okay, now this is combining electron affinity and ionization energy, because we're kind of like, if we're saying how much energy does it take to lose an electron, we're ionizing each of these to lose an electron, so go to F2 plus an electron, to go to F plus an electron. We're taking F minus back to F plus an electron. So for F minus's ionization, it's to go to F plus an electron. And then O2 minus to lose an electron is to go to O minus plus an electron. So O2 minus has 10 electrons, O minus has 9 electrons, so we've lost an electron. And to ionize an electron off of O goes to O plus an electron. So I'm just writing for each of the things here on the reactant side, just lose 1 electron. And so to lose an electron, you increase the positive charge by 1, or if you were negative, you decrease the charge by 1. And so for 2 of these steps here, go to my highlighter mode. For 2 of these, this one and this one, these steps look like electron affinity steps that have been flipped. And so if I flip reaction C, then I get the reaction of F plus an electron goes to F minus. And so that's the electron affinity. So this is like the electron affinity step of fluorine. Now, you might recall the number. I do. I don't know if you guys do. But it's about 300 or so. It's like 328, I think, is a specific number, kJs per mole, and it's negative for the electron affinity. So if I flip that, then this would be plus 328. So I'm just flipping the electron affinity. Now, I don't think you have to have that number memorized. But the question would be, F minus versus F. Which one do you think takes more energy to lose an electron? So if I have F minus, I have a pretty big ion. Electron's pretty far from the nucleus. It has the same nuclear charge making it through that F does. So F minus to lose an electron versus F. It's going to take more energy for F to lose an electron to F plus than F minus to go back to F. Because it's almost like saying, if you think of the electron affinity step, imagine we call this like I0. Like this step here is like the 0th ionization, the ionization of that extra electron. It's like saying that that step has to be less than I1, and continuing the trend for the second ionization being greater. So if you go back to the second ionization is greater than the first, then the 0th ionization is going to be even lower. In other words, if you go to the ionization of F minus to F plus, that F minus's ionization should take less energy. And so which atom requires the least amount of energy? So I hope what I'm trying to say, and hopefully this is being received, that F is going to take more energy to lose an electron than F minus. Because F minus is bigger, has more repulsions. That negative electron's further away from its nuclear charge. And then if we lose the electron, go to F, that the next valence electron's closer to the nucleus, requires even more energy to be ionized. Go to F plus, even closer to the nucleus, takes even more energy for the second ionization. And so I think we can roll out A and B as being the lowest because they're going to be greater in energy than step C. Now, if we're looking next at D versus E and trying to say of those 2 steps, which one requires more energy, it's like for oxygen to have 10 electrons, to lose one to go to O minus, then we lose another electron to go back to O, and then we lose another electron to go back to O plus. Of course, the ionization of O to O plus is going to take a tremendous amount of more energy than O2 minus. O2 minus is huge compared to O. So you're putting that electron really far away from the nucleus, going to require the least amount of energy to ionize compared to O. So just comparing these 2 steps, we can say E is going to definitely require more energy than D, so we can rule E out. Okay, so then our choices come down to C and D. So how do we rank F minus versus O2 minus? Well, and to be honest, like I'm thinking of this problem right now, I probably wouldn't have put this on the packet if I was really thinking, because this is a really hard problem, but it requires a lot of thought. But I think it's productive thought of we come back to like a periodic trend of these being isoelectronic. So those 2 ions have 10 electrons each. And then which one is going to hold on to its electron more strongly depends on the nuclear charge. So fluorine has a higher charge. Oxygen, I don't know, I wrote 10 here. I think I was thinking it had 10 electrons. It's element number 8, so it has a nuclear charge of 8. It's O8. So oxygen only has 8 protons. Fluorine has 9 protons in its nucleus. And so fluorine, having that extra proton, can hold on to that 10th electron more strongly. O2 minus only has 8 protons, so we know O2 minus in terms of size. Let me go back to size real quick. You remember how O2 minus is bigger than F minus in terms of size? That puts that electron further away from its nucleus, and it's more weakly held onto because the nuclear charge is lower. It's going to be a lot easier to lose that electron off of O2 minus.
So O2 minus is the noble gas configuration, correct?
Yeah, and so is F minus, right? So they're both the neon configuration.
So wouldn't that be an extremely large amount of energy to lose an electron? Because you'd have to take it away from that amazing stability, or not?
Well, no, that's an interesting question. I mean, because like you would think that might be the case, you know, because we make such a big deal out of getting to a noble gas configuration. But there's not anything necessarily especially stable about getting to that configuration other than it's better than the alternatives. And then like once you get there, like this, when we get to like lattice energy or think about lattice energy, it's, if you recall, like going from sodium to sodium plus and going from like chlorine to chlorine minus, that those 2 steps there are actually still net energetically high in energy. So like sodium to ionize is about 500 kJs per mole. Chlorine to take the electron onto it is only about minus 350. So that's still plus 150. So that's energetically unfavorable. So what makes that form isn't that going to sodium plus was in and of itself more stable, going to Cl to Cl minus is in and of itself more stable, is that once we get there, we get the electrostatic attraction. That's like 800 kJs per mole. That takes it downhill in energy. And so the stability you get from the noble gas configuration isn't from the configuration itself. It's more from, if you get to that configuration, you get to the sodium plus, you get that interactive force, that force is stronger than if you flipped it or did something else. So if you said, well, why don't we go to F2 minus? Well, it takes a ton of energy. Well, what if you go to sodium 2 plus? That takes a ton of energy. But now you have 2 plus 2 minus, you get back that energy. You don't get it back. So I think something that's really hard maybe to comprehend is that why you get sodium plus chlorine minus and not like sodium minus chlorine plus isn't because it's necessarily more stable to go to the noble gas configuration. It's that once you do, getting there takes the least energy and you get the most back by the forces you get afterwards.
So it's not really important if you have 2 things bonding together.
Yeah, it's like thinking for sodium to go to sodium plus, it still takes energy, even though we say or think having that noble gas configuration is quote unquote more stable. So if it takes energy to create, it's probably not really more stable. So the full picture is what makes it more stable. So the full picture of it doing that, the electron going onto something that's relatively favorable, and then the interactive force you get being energetically then favorable in sum total. Okay, so yeah, so if you get that, that's great, because that's life. I mean, everything in our, like every molecule in existence had the choices to be something else. It ended up being what it is because, at least for some moment of time, the thing that it formed was energetically favorable, if that makes sense. You know, and so that doesn't mean it's going to last forever. That's why we're here for a finite amount of time, because we, like the things like our DNA, our bodies only have so much time before the bonds are going to form something that's more stable, like CO2 and water. So we're stable for the moment because, and you can even say, like this is getting so far off topic, but like if you think of delta G versus delta H versus delta S, and some of you may have learned about this, if not, you'll see it in chapter 19 later, that delta G being negative is what drives a process towards being spontaneous. And so if you think of like human or life in general, there's a lot of order that has to take place. And so you have to have a high energy input somewhere along the way. It's kind of like when you plug your phone in. Like the battery unplugged is being used and depleted, you plug it into a wall, you're then creating a less energetic state that can be used later. So you plug it in, that's pushing the negative delta G to form the reactant substances that you can then later use when you unplug it. That's kind of like what we do to our bodies. It's like you find ways to absorb energy through through delta G negative processes through the inputs of energy, and then when you get rid of the inputs of energy, you use this stored energy to do things. Okay, so getting back to F minus versus O2 minus. F minus is compared to O2 minus. O2 minus is bigger because it has fewer protons. The valence electron in O2 minus is further away from its nucleus, and its nucleus is only an 8 plus. So it's going to take not as much energy. We want to remove the electron. Generally, removing electrons takes energy because there's some reason why the electron's absorbed into the nucleus. are absorbed into the shell of the molecule, so it's going to take less energy for O2 minus to lose an electron. So the lowest one here is O2 minus. I think this would be like the hardest possible question we can ever ask on this topic. So if you're half understanding this, that's great. If you totally get it, that's fantastic. If you're still a little wishy-washy, I wouldn't expect anything like this on the test. I thought this question was a different one when I put it onto this packet. But so the idea of rank ordering ionizations is you can think of electron affinities as being ionizations if you flip the reaction. And hopefully you can get the idea that F minus losing an electron is not going to take as much energy as F, which doesn't take as much energy as F plus. So as you remove electrons, more energy is required for the next successive ionization. Okay, we already did the configuration of lead 2 plus here. Bismuth is 3 plus is just the next neighbor of lead 2 plus. I'm gonna skip this slide here. I think maybe I'll just do lead 2 plus, we'll move off this topic. If we recall, the configuration of lead 2 plus that we did earlier was xenon, 6s2, 4f14, 5d10. And so then, like, that would be the bismuth configuration too, because bismuth is just a 6p3, so if you lose 3 electrons, it's going to lose the 6p3, go to the same configuration that lead 2 plus has. But for lead 4 plus, we lose the next largest electrons, the next n value that's the largest is the 6s2, so we go xenon, 4f14, 5d10. Let's talk lattice energies. And so the idea of what a lattice energy is, it's the energy it takes to separate the ions into its gaseous ions. Gives you an idea of how strong the ionic bond is. So the idea of lattice energies is they're our best approximation of ionic bond strengths. So as lattice energy goes up, our ionic bond strength goes up. But we rank lattice energy as a function of the energy of electrostatic attractive force between our charged particles, Q1, Q2, divided by D. But let's think about magnitudes here. Let's think about magnitudes to get rid of the plus minus. We know we need to have plus minus for attraction. So we know that. So let's think about the magnitudes of charge. So the higher the magnitudes of charge, then the higher the energy of electrostatic attractive force. So 2 plus 2 minus, more strongly attracted together, a stronger energy of attraction. And so by thinking of the energy of attraction, generally it's negative. So I think the magnitude of that attractive force is higher the charge magnitudes, but then also the smaller the ions. So the smaller the ions, the closer they can get together, then the higher the energy it would take to separate those ions because they have a greater energy of attractive force. So we want to have small ions that have the highest possible charges in order to have a high lattice energy to separate those ions. And so for lithium plus versus cesium plus, we're comparing just the size difference because their charges are the same. They're both +1 and -1 ions between CS, alkali metal, versus lithium, and then fluoride versus iodide. So bigger ions have a weaker attractive force. So the lattice energy of cesium iodide is particularly low because the ions are far away from each other. We want the same charge ions to be closer together, harder to separate. And so the simplest idea is if you have 2 attractive particles that are 2 miles away from each other, there's no attractive force there. They want to be as close as they can possibly get together in order to experience the greatest charge. So lithium fluoride has a greater lattice energy because its ions are smaller, but of the same charge as cesium iodide. And then when I have plus minus versus 2 plus 2 minus, I just want to think of the charge. The charge trend is a big trend because when you go from a +2, from a +1, or to a 2 minus from a minus, you're quadrupling the magnitudes of charge. You're roughly quadrupling the lattice energy. If you change the size of the ions, that has a small trend, but not as big of a trend as the charge trend. So I don't even need to think about the size difference. It's not about the relative size of magnesium 2 plus versus sodium plus. It's really just the idea of the charges being different. So as the charge magnitude increases, so too does the lattice energy. So as the charges go up, it takes more energy to separate. And so just remember, the lattice energy is this here, is the energy it takes to separate that compound into its gaseous ions. So it's going to take more energy to separate 2 plus 2 minus ions than +1 -1 ions. So this should be LAF. Let me jump ahead like I want to, this is in the chapter 9 slides, even though it's a chapter 8 question towards the end of that packet. And like, I don't think there's gonna be anything mathematical that we ask you here. Like this slide here was like from an old like version where we used to like really try to teach you guys how to calculate a lattice energy. I mean, there's something interesting from the idea that you can take things like delta HFs, you can take ionization energies of like magnesium, and you can take the energy it takes to break the chlorine bond and the atoms, and you can numerically evaluate all those values and put them together to calculate the lattice energy. Because the one thing that's maybe useful to understand or comprehend is we don't directly study a lattice energy in the lab. You have to indirectly study it through other reactions that we know the enthalpies of or the energies of. But that's maybe nice to understand. But I think the bigger point of trying to understand what a lattice energy is if we kind of start with our picture. Whoop, I'm going to erase. So if we want to start from our picture from elements and really think about the question of from magnesium and chlorine, why would they form magnesium 2 plus and 2 Cl minus ions and form MgCl2 solid? Why does MgCl2, why is that more stable or more likely to find a nature than magnesium and chlorine? And the answer is, well, if you go through the whole process of the ionizations and the bond breaking steps, like if we want to, if we want to go from magnesium solid to gas, that takes energy. So to go from a solid, like solid water to liquid water to gaseous water, that takes the absorbance of energy. So energy has to be absorbed to go to the gaseous atom. If we want to break the bond in chlorine to go to 2 chlorine atoms, that's like breaking a chemical bond. That takes energy too. So it takes energy to break apart chlorine into chlorine atoms. If we then want to ionize an electron off of magnesium to go to magnesium plus, that takes a fair amount of energy. It takes even more energy to go to magnesium 2 plus. And so remember, like we were talking earlier, like, is there anything stable about magnesium 2 plus? It doesn't really look like it yet because it took a lot of energy to get from magnesium solid all the way up to magnesium 2 plus in the gas phase. And then if you think, well, we must get energy back. We must get all the energy back when we make chloride. No, you get some of it, but just a small amount of the energy back when you put the electrons lost from magnesium onto the chlorine atoms and form Cl minus. But you see the picture is that once you make these ions, you then get their electrostatic force of attraction. You then get all the additive forces of these ions being attracted together. And so then you form the ionic solid, and then you get all that energy back. So if you think of the negative of lattice energy, if you think of the idea, if you have magnesium 2 plus 2 Cl minus going to MgCl2, that this, forming the solid, has a delta H or delta E that's much, much less than 0. That's the attractive force that we get that drives the process to take place. So it's the lattice energy or the opposite of lattice energy. That's the explanation for why MgCl2 ends up being more stable than the elements that we start with. Because this is really the overall question is, where does this energy end up relative to where we started? Because if we don't end up lower, we're not going to form the compounds. So the question is, what's more stable, MgCl2 solid or Mg and Cl2? The answer is forming the MgCl2 as the solid. Now again, like, this would be an interesting example to take a huge detour of why not Mg2 minus and Cl plus? Well, it's going to take a lot of energy to create the 2 minus ions. It's going to take a lot of energy to create the ions, the Cl plus instead of Cl minus. And then we're never going to get back enough energy to make the product more stable. So it's really just a question of if you can picture something else you could have done, does it end up being more stable than MgCl2 solid? I doubt that it does. Now, let's end with just making sure that we can go from a simple Lewis structure into a molecular geometry and making sure that we understand the process here. And hopefully this is relatively straightforward. If I want to get a Lewis structure, like if I want to think bonding domains, non-bonding domains, I got to do a Lewis structure. So I'm counting my valence electrons. I have to add 2 for the negative charge. So that's 26 total valence electrons. If I screw the valence count up or if I don't do it, I'm probably never going to get a Lewis structure right. So I do this so that I can then single bond my oxygen atoms to sulfur and then distribute enough electrons for an octet around the non-central atoms first. And so then I count 8 electrons on each of the O's. That's 24 electrons used. 2 electrons left over, I now know that those go onto the central atom. So if I was comparing this Lewis structure to that of just SO3 without the 2- charge, this only has 24 electrons and wouldn't have the lone pair electrons on sulfur. And so now for SO3 2-, I have 1, 2, 3 bonding domains and 1 non-bonding domain. So I have 4 total domains that are 3 bonding domains. So 3 bonds here and plus 1 non-bonding domain. Now we're out of time real quick, but if you were thinking, should I have made a double bond or 2 double bonds, or should I consider double bonds? You see how that doesn't change the number of domains. If we make double bonds or single, we still have 3 total bonding domains. And so then what's the geometry taken? It has to be tetrahedral, so it's based on the total. So we have a sulfur, picture a tetrahedron, and then lone pair in one of the spots, oxygens in the other. What's the shape here? Trigonal pyramidal. All right, so that's where we'll end for today. I'll go through some of the remaining problems in this packet to review on Monday. Stop by on Zoom if you want to on Monday. Take care, guys. Have a great weekend.
Do you have to remember all the
Remember later.